Yeah, so first I would like to thank the organizers and Professor Shawnee Goon for giving me the opportunity to talk here. So today we'll talk about high dimensional time series model and its asymptotic. This talk is based on joint works with my PhD supervisor, Professor Arup Bose, but most of the part is not part of my doctoral thesis. It's done after that. Yeah, so we'll start with a linear time series model. So here xt and epsilon t, these two are vectors of length p. And as you can see that xt can be written as linear combinations of q many past epsilon t's. So this is moving average process, and this is the coefficient matrices, the Xi JP. These are all P cross P coefficient matrices. We'll have certain assumptions on the process epsilon T and therefore on XT as well. So the assumptions on epsilon T's are IID across T, and their entries are also IID with mean 0, variance 1. Later we can relax some of this assumption. We'll see that later. And as epsilon T is a driving process, of course, we'll not observe epsilon T directly, but we'll observe XT, which will be made of epsilon T here, and therefore epsilon T is called driving process or innovation process. And we'll also consider that Xi JP to be non-random, that is, they are deterministic. We can have that to be random also, but if we consider the Xi JP, if it is random, we can consider Xi JP is independent of epsilon T. Then some conditional argument will give us the similar result that I will discuss here. And also we'll assume that, so for some technical reason, we'll assume that epsilon TP and Xi JPs are nested. So by that I mean that if we consider epsilon TP plus 1, that will be a vector of length P plus 1. And so first P component of epsilon TP plus 1 will give us epsilon TP. And similarly, if we consider Xi JP plus 1, that will be a square matrix of order P plus 1. And its first P rows and P columns will give us Xi JP. So in this manner, they are nested. But even if they are nested, XTPs are not nested, because you can see that each component of XT can be written as a linear combinations of all the components of epsilon T. And say therefore, even if epsilon T is nested, all the component of XT will get changed if we go from the pH stage to the P plus 1 stage. So therefore, XTPs are not nested at all. And here we consider Q, so it looked like finite, but it can be infinite also. Then it will be, the sum will be from 0 to infinity. So in that case, we need additional restrictions on the coefficient matrices. So the restrictions are something like that we can take spectral norm of this matrix or 1-1 norm of this matrix. It depends on which type of problem we are dealing with. Based on that, we'll take the norm, whichever is convenient for us. So we'll take the norm on this matrix, and then we'll say that sum of j equal to 0 to infinity of the norm of the Xi j matrix will be finite. So this kind of assumption we need it if we assume that q equal to infinity. If q equal to 0 and Xi naught p, that is Xi 0 p, that is identity matrix, then we'll get xt equal to epsilon t, this kind of model, which is epsilon t's are all IID. So therefore, this will give us a IID process. So MA0 process corresponds to IID process. And we all know that in time series, the well-known linear time series models are autoregressive process, that is AR process, and autoregressive moving average process, that is ARMA process. And these two processes can be written as moving average process of order infinity under certain causality condition. So that happens in finite dimensional setup. In high dimensional setup, there is also certain causality condition, which is of course not exactly same as that we have in finite dimensional setup, a little bit different than that. But there is certain causality condition that exists in the literature, under which we can express AR process and ARMA process in terms of MA infinity process in high dimensional setup as well. And therefore, MA infinity process is a more general model to talk about when we'll deal with linear time series model. And we are in high dimensional setup, so we'll assume that dimension will grow along with the sample size. Here we assume that n is our sample size and p is our dimension. So here you can see that xt and epsilon is there all p cross 1 vector. So p is our dimension and n is sample size. So we assume that the dimension growing along with the sample size. So it's in this manner, and the growth rate is like this, that dimension grow at the same rate with the sample size, that therefore p by n converges to y, where y is strictly greater than 0 and less than infinity. Now, there are other high dimensional regime also where y equal to 0, that is dimension grows slower than the sample size, and this dimension can grow faster than the sample size, where y will be equal to infinity. So here we'll talk about, in this talk, we'll mainly focus on the first case where y is strictly between 0 and infinity. And there are certain works in y equal to 0 as well. I will provide reference for that. I mean that whatever problem I will discuss here, for that there is work for y equal to 0 as well, and I will provide reference for that. And these two regimes are very different. It's not like that whatever we are getting for y greater than 0 case, we'll put y equal to 0 there and we'll get some meaningful result for y equal to 0. It's not like that. So there is a different type of challenges there and different type of result which will come out to be meaningful in this y equal to 0 regime. One can think of that if p is much smaller than n, that is p by n going to 0, unless p is not fixed, it's not an easy problem. So the asymptotic regime is completely different and we need to deal with it separately. And of course, there is regime which is much more difficult, where p by n going to infinity, and there are certain sub-regime of that, log p by n going to 0, and there are many. And depending on the problem, we'll consider different type of regime, and we can work on that. So whatever problem I will discuss here, for that p by n going to infinity case is not well studied till yet, and there are a lot of problem open in that direction. So this is our model. Now you can see that we can see that this model is strictly stationary model. So basically we'll assume that we are observing x1, x2 up to xn. Of course, the dimension will be pn then when we are observing n many time points. But it doesn't matter. We can actually observe any consecutive n many time points because it is strictly stationary. So for the convention, we are assuming that we'll start from t equal to 1 and we'll end at t equal to n. And of course, if n increases, we will going on increase our sample size, and with the same pattern, we'll observe the data. So this is this model, and we know that what kind of observations we'll have. Now, as it is strictly stationary, is also weak stationary as well. So therefore, the key quantity to study for these models are autocovariance sequences. So the population autocovariance sequence of order or lag u is defined here. It is expected value of xt into xt minus u star. So in throughout this talk, whatever matrix or vector we'll assume, they're all real. So therefore, by star, I basically means it's transpose. And looking at this, you can see that this is basically covariance between xt and xt minus u, because here the mean of epsilon is a 0. So therefore, it is basically the covariance between xt and xt minus u. And as it is a weak stationary, it will depend only on u but not t. So therefore, here in the notation, I make it a function of u only. And this is a p cross p matrix. And by the definition of moving average process that I gave in the last slide, it turns out like this. So this is a p cross p matrix. Now its sample count. So this population autocovariance matrix is basically the parameter of the model. And if we consider its sample counterpart, then it is I denote it by gamma hat u, and it is nothing but the sample counterpart. So expectation is replaced by the sample average. So this is called the sample autocovariance matrix of order or lag u. Now u equal to 0 corresponds to the dispersion matrix. The u equal to 0 will come, and 0 will give us a population dispersion matrix or population variance covariance matrix, and gamma hat 0 will give us sample dispersion matrix or sample variance covariance matrix. Except for u equal to 0, all these matrices are not symmetric. That is also clear from the definition. Now, in statistics, the obvious question here, whether gamma hat u can consistently estimate gamma u or not. So, if it is finite dimensional, then the answer is yes, because the point-wise convergence, or the entry-wise convergence is enough to guarantee consistency. So, in finite dimensional setup, gamma hat u, of course, will consistently estimate gamma u. But in high dimensional setup, it's not. There are many problems regarding the number of growing parameters, because dimension is increasing, and therefore the number of unknown observations in gamma u, that is going to be increased. So therefore, in high dimensional setup, gamma hat u will not be at all consistent for gamma u. And for that, we need extra treatment, that we need somehow restrict our parameter space. And for different parameter space, we need different type of regularization on sample autocovariance matrices. And after that, we can get the consistent estimator. And this kind of problem has been well studied in the literature. this started around from 2010 to 2018. So in this time, it has been well studied in the literature. There are very few problems still remains in these directions. So, but I'm not going to the details of this estimation problem. I will discuss some other thing. So here is our goal. So our goal is to study limiting spectral distribution of symmetric polynomial in sample autocovariance matrices. So what is limiting spectral distribution? That I will discuss in the next slide. Now the next point is why I'm interested in symmetric polynomial in sample autocovariance matrices. Now we can consider the non-symmetric polynomial as well, but in random matrix theory, finding out the limiting spectral distribution for any non-symmetric matrices is very difficult, and there are very few results known in this direction. So therefore, when we started dealing with the high-dimensional linear time series model and then started exploring its asymptotic, then we thought that to make our life simple at the beginning, let's take the symmetric polynomial. Of course, one can take non-symmetric polynomial as well, and the problem will be difficult in that case. So here I'm concentrated only on the symmetric polynomial in sample autocovariance matrices. And why I'm interested in this kind of problem? Because that will help us in many statistical applications, like determining the unknown order of the moving average and autoregressive process, testing for white noise and testing for coefficient matrices. So we'll not, due to the interest of time, I will not go through the these applications here, but I will give a short view or graphical idea of determining unknown order of the moving average process, so that one can understand why this kind of problem is important in statistics. Now this I will discuss based on this paper, where so in this paper we consider the dimension is growing at the same rate with the sample size. The same thing when p by n converges to 0. So the second paper deal with the second case. And so the material are all given there, but I will mainly concentrate on the first one here. And of course, we'll give some idea for the second one as well. Okay, so now I will define what is limiting spectral distribution. So limiting, suppose RP is a P cross P real symmetric matrix. So it is a real symmetric, so all its eigenvalue has to be real. So suppose lambda 1, lambda 2 up to lambda P, they're all eigenvalues of RP. Then empirical spectral distribution is nothing but a discrete probability distribution which put mass 1 by P at each of its eigenvalues. So therefore, it is a discrete probability distribution, and along with P, it will give us a sequence of probability distributions. Now, if this sequence of probability distribution converges weakly to some unique probability distribution, then the limiting probability distribution is called limiting spectral distribution of RP. So this is a definition of limiting spectral distribution. For example, if we have the identity matrix, so therefore all its eigenvalues are 1, so its ESD is degenerated at 1, and therefore its LSD will be also degenerated at 1. Now suppose we have a matrix, the diagonal matrix, which has 1 and -1 alternatively, then of course we'll have approximately half of the mass, of course half plus minus small o p. So this kind of mass will be there for small o 1, half plus minus small o 1 amount of mass will be for plus 1, and the same for the -1. So, and therefore if we take the weak convergence thing, so we'll get the so LSD will be a discrete probability distribution which has mass at 1 and -1, and each of them will have mass with amount half. So this will be in this way we can find out the limiting spectral distribution. Of course, I gave the example of very easy matrix. So for difficult matrix, it will be difficult to find out, but one can find out algorithmically. So now if RP is a random matrix, so in our case, we'll basically deal with the sample autocovariance matrices, so which will be a random matrix. So if RP is a random matrix, then all its eigenvalues will be random, and therefore the ESD that we'll get, this sequence of probability distribution will be all the random sequence of random probability distributions, and therefore the weak convergence of ESD to LSD should have in some stochastic sense, that is either in probability or in almost sure sense. So here in this talk, so whatever result I will discuss, or LSD result I will discuss, all of them will be in almost sure sense. Also, we can make this matrix to be non-symmetric. In that case, we can get the eigenvalues in the complex plane, and we'll have this ESD will be supported on the complex plane, and we can have the weak convergence on that space only. So in that case, ESD can also converge to some unique probability distribution which is supported on the complex plane. So these are all things. I mean, this definition is also valid for, or can be written for the symmetric matrix as well. But as here I am interested only for the symmetric matrix, I will talk about only. So therefore, the definition I give only for the symmetric matrix. Okay. So next I will show some figures and we'll discuss some statistical applications. So here you can see that is a moving average process is xt equal to epsilon t, and we compute the symmetric product of sample autocovariance matrices. You already see the definition of gamma hat u, and gamma hat u transpose we can find out and we can take the product. So this is symmetric product of sample autocovariance matrices. And CDF means cumulative distribution function. So here we plot CDF of empirical spectral distribution of this random matrix. We know, so in the previous slide, we have already defined what is the empirical spectral distribution of a matrix and random matrix. So we'll find out empirical spectral distribution of this symmetric product of sample autocovariance matrices, and then is a probability distribution. So therefore we can find out its CDF. So here we plot that. And I plot it for u equal to, that is for order u equal to from 1 to 4. And it is for n equal to p equal to 300. So we actually try for more n and p, and we have seen that already convergences occur because all the figures look same. So therefore here I take only one figures, but of course the convergence occurs. So there is no point of showing the other figures. So you can see that all the ECDF coincides. So this gives us a conjecture that if we consider moving average process of order 0, then LSD of symmetric product of sample autocovariance matrices are going to be identical for u greater than equal to 1. Now next I'm considering moving average process of order 1. Here of course we have a coefficient matrix, and that coefficient matrix I take to be 0.5 times identity matrix. So its LSD is degenerated at 0.5. One can clearly see. And again, for this type of process, I consider the symmetric product of sample autocovariance matrix and plot its ECDF for u equal to 1, 2, 3, and 4 in the same graph. And you can see that there is a separation for u equal to 1, but again the coincidence occurs for u equal to 2 onwards. So then we can again make the conjecture that if we have moving average process of order 1, then LSD of symmetric product of sample autocovariance matrices are going to be identical for u greater than equal to 2. Here we consider another moving average process of order 1, but the coefficient matrix is much different than previous one. Here the coefficient matrix is 0.5 multiplied by IP plus AP. IP is identity matrix of order P, and JP is a P cross P matrix whose all entries are 1. So therefore BP is a matrix whose is a P cross P matrix whose diagonal entries are all 1, and all the off diagonal entries are 0.5. So we know that except for 1, all the eigenvalues of the matrix BP is 0.5. So therefore, its ESD will have mass 1 minus 1 over P at the point 0.5, and there are other eigenvalue, so which is of order P, which will have mass 1 over P. So this will be the ESD, and it will converge weakly to the limiting spectral distribution that will have degenerated at 0.5. So in both the cases which I show here, so here also we get the LSD degenerated at 0.5. Here also I get the LSD degenerated at 0.5. But the matrices are quite different. But you can see the figures are almost same. If you compare these two figures, the figures are almost same. So this gives us another conjecture that even if the coefficient matrices are different, but if their LSDs are same, then we are going to get the same LSD or the identical LSD for the symmetric polynomial or symmetric product of sample autocovariance matrices. And here also we'll get the same phenomena that it looks like that the symmetric product of LSD of symmetric product of sample autocovariance matrices are going to be identical for u greater than 2 when we have MA1 process. And next I'm considering MA2 process. So here you can see that we need two coefficient matrices. So one coefficient matrices I take CP, there is a diagonal matrix which has 1 on half of the diagonal and minus 1 on another half of the diagonal, and there is another matrix DP which is of this form. This basically DP is also a P cross P matrix. So now if so it has all the entries all the entries 0 except few entries that I am saying now. So its first row last entry will be 1. Then the second last entry of the second row will be 1, and in this way the first entry of the last row will be 1. So it has 1 on the opposite diagonal, and one can show that for both these matrices the LSD are identical, and this LSD has two mass, 1 and -1, and in both the mass we'll have the probability half and half. And also one can show that this CP and DP, these matrices are not simultaneously diagonalizable. Why I'm telling that will be clear later. So they are not simultaneously diagonalizable because these two matrices are not commutative. So these are the, because of this nature of CP and DP, we consider this model, and why I'm considering that will be clear later. And here also we did the similar type of thing, and we can see there is a separation for u equal to 1 and 2, and coincidence occur after u greater than equal to 3. So that is for moving average process of order 2. So from there we can say that suppose we have data and we know from it is from moving average process of it is from some moving average process, then we can compute symmetric product of sample autocovariance matrices, and we can plot it in the same graph for certain order, and we can search for a cutoff after which the coincidence occur, and this cutoff can be served as an unknown order of the moving average process, and if there is no such cutoff, then we can say that it is from moving average process of order infinity. So this is a rough idea that how we can determine the unknown order of the moving average process graphically. Okay, so that is why this kind of problem is important. Now here we can see that here we have the polynomial of a particular type, but if we consider the testing for white noise process, we may have to use the, we have to use the polynomial which involves more than one order of autocovariance matrices at the same time. And of course, if we want to compare between two independent time series model, we may have to deal with the polynomial of sample autocovariance matrices of two different or two independent time series models. So basically, we need to deal with the symmetric polynomials, all types of symmetric polynomial in sample autocovariance matrices together. So that is why we interested in this model or in this type of problem. So now we'll discuss what is the existing results. So before going to the existing results, I'll try to recall the Strelitz transform. So here is the definition of Strelitz transform. I'm not going line by line, but why it is important. So Strelitz transform is also the similar property like characteristics function, that it has one-to-one corresponds with set of all probability measure, and also the point-wise convergence of Strelitz transform imply weak convergence. So it's like the characteristics function. So but why I'm discussing it here, because in nanometrics theory there are two type of approach to deal with limiting spectral distribution. One is Strelitz transform method and another one is moment method. So in the existing literature mostly deal with Strelitz transform method, and they end up or they give the description of their LSD in terms of its Strelitz transform, and that is why I want to define it here or recall it here. So here is the result. So the first result in this direction is by Jean, Wang, Bai, Nair and Harding 2014. This is an analysis of applied probability paper. So I will give the reference later, the details reference. And so they consider moving average process of order 0, and they consider XT to be IID across T, and the entries of epsilon T's are all IID, mean 0, variance 1, and have finite fourth order moment. They consider dimension grow at the same rate with the sample size, and under all this assumption, they prove this result. That is the LSD of symmetric sum. So so when we show the figure, we show for the symmetric product, but they prove it for symmetric sum. So LSD of the symmetric sum of sample autocovariance matrix for order greater than equal to 1 exists, and its Strelitz transform is a solution of this equation. Now the thing is you can look at this equation. This is a polynomial of degree 4. So therefore, it will have 4 roots, and only one root will satisfy the property of Strelitz transform of a probability distribution, and that root will be the solution here. And the second thing is why they consider u greater than equal to 1 but not u equal to 0. So for u equal to 0, it is basically the sample variance covariance matrix for moving average process of order 0, rather IID process, and for that the LSD exists, and this LSD is a very well-known Marchenko-Pastur law with parameter y, and is a very old result in nanometrics theory that is already proved in the literature far ago. So therefore, they consider only for u greater than equal to 1, and they prove this result. Now also you can see, looking at this equation, you can see that this equation doesn't depend on u. So therefore, this will provide us or this proves that if you consider the symmetric sum of sample autocovariance matrices, then their LSDs are all identical for u greater than equal to 1 if we consider moving average process of order 0. So this actually proves the conjecture for symmetric sum. Of course, we saw it in the figure for symmetric product. So we'll come to that. but they prove it for symmetric sum. Now I'm considering the next result in this direction, which is by Liu, O, and Paul in 2015. They consider the similar assumption on the driving process like the previous one, and they have the coefficient matrix because they consider moving average process of order Q, not MS0 process. So they consider this Xij matrix, the coefficient matrix, as symmetric, norm-bounded. Norm-bounded means its largest singular value is bounded away from 0 as p going to infinity. And then Xij's are simultaneously diagonalizable, but we have already seen that even if it is not simultaneously diagonalizable, we'll have the result, at least in the figure we have seen. And there are certain technical assumptions that I'm not going through. And also they consider the dimension or the regime that p by n going to some constant y, which is strictly greater than 0 and less than infinity. So under all these assumptions, they prove this result that the LSD of symmetric sum of sample autocovariance matrices exists for moving average process of order Q. Q can be infinity as well. So they prove this result. Of course, this equation is very cumbersome. I'm not going through because once you are not in this type of thing, you will not be able to understand what this equation means. So I will not discuss that at this point. And this equation is actually difficult to deal with. And there are many things that we cannot basically find out of this equation. Or maybe it's possible to find out, but it will be difficult. Later, we'll see that how we can deal with some alternative thing. And the similar result for p by n going to 0 is given in Wang, O, and Paul 2017 paper. And as you can see, they consider only additive symmetrization of this matrix. Now, so this Liu, O, and Paul, this paper is 2015 Annals of Statistics, and this paper Wang, O, and Paul 2017, that is a Bernoulli paper. I will give all the references at the end. Now, we'll see that what kind of thing we can deal with. So first thing is we can drop the simultaneously diagonalizable assumption that we already shown in the figure, but technically also we can drop these assumptions, and we do not need this Xij to be Hermitian or symmetric. It can be any non-symmetric matrix as well. And we can consider the other kind of symmetrization, like not only symmetric sum, symmetric product, or any other kind of symmetrization like gamma 1, gamma 2 star, then plus gamma 2 plus gamma 1 star. This kind of symmetrization also we can consider, which basically involves more than one order at a time, the third point. And also we can combine more than one independent time series at a time. And so all these things we can do in a unified way under the same umbrella. And so this is because of so basically matrices are all non-commutative object. So therefore we can actually take help from the non-commutative algebra and phi probability, and which actually help us to deal with all these things under the same umbrella. So so basically we use certain tools from phi probability theory and non-commutative algebra there. Okay, so I'm skipping this these two slides because of the time. But I just wanted to mention that as I've already mentioned that there are two methods, Sturgeon's transform method and moment method to establish limiting spectral distribution of a symmetric matrix. So Sturgeon's transform method is basically deal with a particular matrix one by one, because it has to deal with some recursion relation, which is matrix, I mean which type of matrix we are considering, so matrix dependent. So it cannot deal with all the things together. So it is basically a case by case method. So therefore we cannot, so whatever method used in the literature, this Sturgeon's transform method is not useful if we want to do everything under the same umbrella. Whereas the moment method is useful, where basically we deal with the convergence of this kind of thing, where RP is a symmetric matrix, so therefore RP power H will be also a symmetric matrix, and basically expected average stress. So we'll take the convergence of this kind of quantity, and the non-commutative algebra, if we make the algebra made by all the matrices, so we'll get all the polynomials there, and if we consider the state to be the expected average state there, trace there, so that will help us to get the convergence of this kind of thing, and which help us with this in the moment method will help us with this point, and this will give us a way of doing all these things together. So I'm not going, so this is basically the method that how we can get the limiting spectral distribution. I'm not going to the technicalities at this point. And this is our result, that we consider that epsilon t's are all independent. So entries are all independent. We don't need identically distributed, and their mean zero variance 1. All moment exist we'll assume, but we can relax this assumption later. And this we need because we deal with polynomials of all the degree together. And we'll have certain condition on the coefficient matrices which are much more weaker condition than what we have in the literature previously. Under all these conditions, we prove that the LSD of symmetric product of not symmetric product, LSD of all symmetric polynomial in sample autocovariance matrices exist, and the limit we can express in as a function or polynomial of freely independent variable which is coming from non-commutative algebra, and that basically help us to deal with many things. So from there we can basically prove that the LSDs are identical for symmetric product and symmetric sum if U greater than equal to Q for moving average process of order Q. This kind of result we can very easily prove from this type of descriptions. And similar result for P by N going to 0 is there, but we need additional centering and scaling. We can relax assumption A2 because if we consider symmetric sum, we need only 4th order moment, and symmetric product, we need only 8th order moment. So we can relax these assumptions also. And all the previous results that we discussed that will follow the special case of our result. For Q equal to infinity also we can deal with, but for only for symmetric sum and symmetric product. And this result I have already discussed, this identical thing that we already see in the simulations. So that also can be proved technically as well. And these are the paper where we deal with the independent, more than one independent time series model together. And so these are the references that I talk about, the existing results. Thank you.
Please feel free to ask questions and give your comments now. Okay, no question. I have one small question, Monika.
Yes. Yes.
Could you please shed some light on possible fields of applications of these findings?
Yeah, so for example, so I show one graphical applications like how to determine the unknown order of the moving average process. Now we can also think of the testing for white noise. For example, if we test for the white noise, what we'll take usually? So in univariate setup, we'll take gamma u star, this kind of thing, and take you some kernel. We'll take the some kernel weight and then take sum over u equal to starting from 1 to up to a certain level, which is also going to infinity as n going to infinity. So we'll take a growing range of the autocovariance and we'll see whether that is 0 or not, and that we see together, and that will of course increase as n going to infinity. This kind of statistics we'll take. So basically we'll take the polynomial in univariate. Now if we have the multivariate or setup, then that will give us a matrix polynomial, and if we get the LSD result of that kind of polynomial, and after that we can also by this by product of this LSD result we can also prove asymptotic normality of trace of such polynomials, and by that we can propose a test for white noise in high dimensional setup.
Okay. Thank you. Let's thank Monika.
Thank you.